Hello. Today we are going to discuss uh, stable isobar formula. How this stable isobar formula is derived from a semi-empirical mass formula. For that, we need to discuss first some basic key points of a liquid drop model. So therefore, I'm going to discuss first a liquid drop model key points only. Later, quickly, I'm going to derive the semi-empirical mass formula. After that, we can find this formula. Okay. So this is very important. So many CSIR net gate questions are asked by using this formula. Okay. So this is very important formula in nuclear and particle physics. Nuclear physics, not particle physics. Nuclear physics. Okay. So today our aim is to derive this stable isobar formula. That's it. Okay. So liquid drop model. So just I'm going to discuss here the just outline points only. Okay. Not theoretical revision. Liquid drop model. Okay. So the first point is liquid drop model. This model is proposed by Weizsäcker. Is a famous physicist, German physicist, and this liquid drop model is developed by the Bohr and Wheeler. Nuclear reassemble a liquid drop. It could explain nuclear fission successfully. It gives very important formula that is semi-empirical mass formula. So let us try to spend little bit time the similarity between the nucleus and the liquid rock. So similarities nucleus and liquid rock. If you want to derive semi-empirical mass formula, then you need to remember all these points. Okay. First similarity between nucleus and liquid rock, nuclear forces. Here surface tension. Density of nucleus is constant. Here density of liquid is constant. The binding energy. Here latent heat. We already know that what is latent heat. So latent heat, one is fusion, another one is vaporization. Here the nuclear disintegration is happening. Here evaporation. These are the similarities between nucleus and liquid drop. Now it's time to derive the semi-empirical mass formula. So we know binding energy B equal to ZMP plus neutron A minus Z into M minus M is a capital M. Okay. So this capital M is this mass is function of A and Z, right? So I'm going to use this M. By using the formula, I'm going to write this one like this. ZMP plus A minus Z Mn minus P. Okay. So based on this, mm, this binding energy, okay, uh, almost five terms are there. Five terms. So you already know, right? Binding energy. What is binding energy of the formula? So this is just binding energy. Okay. Very good. So it is better to classify like this. The five terms I'm going to use. One is volume energy. Second one is surface energy. Third one is Coulomb energy. Here energy binding energy. Okay. B A means symmetric energy. Sorry, asymmetric energy. And the final one is pairing energy. The first I'm going to derive this volume energy. Number one is volume energy, right? So volume of the nucleus is proportional to A, right? Okay, number of particles, it will be protons plus neutrons, right? This mass number. The then the B divided by A equal to the constant. Okay. B equal to AV into U. So this is the first step. I'm not giving here step-by-step derivation, just bullet points. Second one is surface energy. So as volume increase, volume of nucleus is increase. One thing we understand here, the surface area, so this volume, right? The surface area, okay? Surface area is increased. Hence, number of surface nucleons also increase. Nucleons also increase. Hence, here binding energy going to the decrease. So we need to know whether this binding energy is decreasing or this one is binding. Okay. Here the binding energy is decreased because they can't interact with the many number of nucleons. So therefore here the binding energy is decreased. So here the binding energy is proportional to the minus 4 pi r naught a 2 divided by 3. In case if you want to know this how this formula is coming, b is proportional to 4 pi r square, right? So this is the first step. By using this step we can have this formula, right? So in case if you want to know the radius of the nucleus, r equal to r naught a power 1 divided by 3, right? So this is the final formula. So by using this one, we can write binding energy B equal to this one. I'm considering all these one terms, not minus, okay? AS because of surface energy, AS star. A power 2 divided by 3. This is next one. So remember here, the binding energy is decreasing here, surface energy. Next term is Coulomb energy term. We need to find the Coulomb energy term. So Coulomb energy, which we denoted B suffix C, right? We know the nucleus X, A, Z. Okay. The number of protons, for example, the number of neutrons plus protons are there. For example, number of protons are there here. So if you want to know number of protons pairs, for example, Z, C, 2. I can write like this here. Z into Z minus 1 divided by 2. So the Coulomb energy E equal to the constant K, Q1, Q2 divided by R. Okay, R. The force is 1 divided by R square. The potential energy is 1 divided by R, right? So Q1, Q2 divided by R. So therefore, I want to know what is Q and what is Q1. Okay, that equal to, here I'm going to write this one. The number of pairs is one, right? Number of pairs. The K E square Q1, Q2. Okay, divided by R. Place of Q1 is E plus, right? In case electron is there, we can use minus E minus C. Proton is plus E, right? Plus E, E square. Then how many number of pairs are there? Proton pairs. Z into Z minus 1 divided by 2. So now you can use the basic uh, nuclear radius formula. The K E square first term divided by R naught A power 1, sorry, 1 divided by T, not 2 divided by, and Z into Z minus 1 divided by 2. I hope you can understand this one. I'm going to consider this one is constant. Okay, so minus p suffix c because of Coulomb interaction, right? Minus a suffix c z into z minus 1 divided by including this 2 also, sorry, I forgot. So a we can write like this, a power 1 divided by 3. Constant minus cs is square including these 2 also. This is the Coulomb term. Next, symmetric terms. Due to the symmetry in the number of neutrons and protons, binding energy we can write like this. Fourth term is symmetric. Symmetric term. It is denoted by B suffix A. Okay. So due to asymmetry in the number of protons and neutrons, the net binding energy of the neutron we know that n equal to A minus Z. This neutron number. Asymmetric binding energy is proportional to, sorry, n minus Z whole square divided by A. Or else we can write this one is proportional to A minus 2Z, because of in case if you use the in place of an A minus Z, then you can get this term Z squared divided by A. So this proportionality constant, I'm going to use here the asymmetric minus A, okay, A minus 2Z divided by A. This one is whole square. This is fourth term. This is fourth term. And fifth term is pairing energy is very, very important. Fifth term is pairing energy. Pairing energy. So nuclei here, if we consider this nuclei, for example, even, even, the number is atomic number, the 150. In case if you observe odd even or even odd, okay, the number is 52, 55. And if we consider the odd, number 5. So the pairing energy term is, so B suffix P equal to A P A power minus 3 divided by 4. This is the pairing energy term. So here this pairing energy A suffix P is we can write into t terms. One is plus 1, another one is 0, another one is minus 1, depending upon the pairing energy. And we can use this plus 1 minus 1. We will discuss later these terms. Okay. So our aim is to find the stable isobar formula, right? So therefore, the binding energy formula, which I'm going to add, two terms are positive, three terms are negative, right? Binding total binding energy of nucleus, volume energy, surface energy, a power 2 divided by 3 minus Coulomb energy, z into z minus 1 divided by a power 1 divided by 3, asymmetric, a minus 2z whole square divided by a. Last one is the pairing, minus 3 by 4 here. Okay. So here, for example, if you want to a stable isobar total binding energy of system, we can reduce stable isobar, right? Stable isobar, one isobar. So you can minimize this one in terms of z equal to 0. Then this term is 0, this term is 0, and this term is also 0. Remaining two terms also we can write like this after derivation. The minimizing with respect to z binding energy formula, okay, with respect to z equal to first term is 0, second term is 0, third term is here the z is there, z minus 1. Then we can write this one like this, okay. After derive this one, then you can get this type of term. So I already simplified. Directly I'm using this formula. Next, the 2a z minus 2z, if you consider like that, then you can get the situation is like this. Okay, this is the 4s, 4as minus is there, a minus 2z divided by a. Last term is 0. Okay, so this term is equal to 0, right? So minimizing, if you want equal to 0, then so it is better to write by using these two terms. I'm going to write like this: 2acz divided by a power 1 divided by 3 equal to 4as a minus 2z divided by a. Anything is there cancel? Okay, here the 2 is there, here the 4 is there. Remaining term a suffix c z divided by a power 1 divided by 3. So 2as a minus 2z divided by a. Then I am going to write this equation like this after simplifying: a1 divided by 3 and this one a divided by 2as, okay, this portion, and a minus, I'm going to 2z divided by z. This z is there here, I'm using here. Okay. So if you look at this equation, a suffix c divided by 2as, this term, and this one I'm going to use like this: a 2 divided by 3 equal to this one a divided by z. After splitting 2z divided by z, this z will cancel, and remaining portion is Here the minus 2 is there. So suppose I'm going to write this minus 2 here. A sub x divided by 2as. Uh, it is better to write like this: 2 divided by 3 plus 2 equal to, because here minus 2 is there, a divided by z. So here I want to only z, that is a stable isobar formula, right? So z equal to, is easy, right? A divided by 2, sorry, not 2, a divided by ac divided by 2as, okay, a power 2 divided by 3 plus 2. This is a very, very important formula. So by using this formula, you can calculate many CSIR net gate problems. Okay. For example, for example, uh, binding energy of nucleus is given by, they are giving the binding energy formula. So for your purpose, I'm going to okay, they are giving one binding energy formula here, the nucleus binding energy. They are asking to find the uh, Z for the stable isobar. Okay, so they are giving here the one problem. The problem we can write here, the binding energy be 16a minus 20. This is previous year question. Okay, CSIR not get problem. 3 divided by 4 z square a 1 divided by 3 plus 30 n minus z divided by a whole square. This, they are giving this binding energy of nucleus. Then they are asking to find the value of z for a stable isobar. Stable isobar. So we already know the formula here. The formula is there. The z equal to a ac divided by 2ac. We need to find the what is a Coulomb term and the asymmetric term, symmetric term. Okay? This symmetric term. Sorry, not symmetry, asymmetric term. So by using this term, this is volume, Coulomb, asymmetric, pairing, right? Okay. So carefully, if you look at this thing, then we can observe this is pairing. Okay. Asymmetric. So A C equal to, using the our binding energy formula, and this one, our binding energy formula is there here, the A minus Z. Okay. 3 divided by 4 as per given question. Asymmetric minus 30. This is minus 30 asymmetric value. So this is 3 divided by Coulomb value. Okay. So for that we need to compare this our well-known binding energy formula and the given binding energy formula. Therefore, we can easily find out these terms, Coulomb terms, asymmetric term, pairing term. Okay. The formula is Z equal to A divided by 2 plus AC Coulomb energy, asymmetric energy, into A power 2 divided by 3. Okay. So they are not giving any number A, this mass number. So the options are the A divided by 2 plus this one is 3 divided by 4 plus into this one is minus 30 into A power 2 divided by 3. So in case if you look at this one, In this one 30, here the 10. Okay, the 4 is there, here 8, total 80 here. That equal to a divided by 2 plus 4 8. Minus is there here. Just right. Okay, minus 1 divided by 80, a power 2 divided by 3. So a divided by 2. In case if you comment the 2 here, the 2 1 minus this is double, right? 160. So I'm going to, this is only 2 divided by 3. Okay, so z equal to a divided by 2, 1 minus a 2 divided by 3 divided by 16 inverse. This is the answer. Okay, so like that you need to find one more problem here. Okay, so in case that if they are giving the mass number value, okay, so we need to try this question. Binding energy, they are giving like this: binding energy B equal to A is 2 divided by 3 minus, this is symmetric, 2z minus A whole square divided by A minus AC z square divided by A power 2 divided by 3. If they're giving specifically here the volume term 16 mega electron volt, symmetric term 16 mega electron volt, this symmetric term, sorry, this is a surface term, not a symmetric, surface term. This is symmetric term 24 mega electron volt. Then the Coulomb term is 0.75 mega electron volt. They are asking find the Z value of the table isobar for the specifically mentioned A equal to 216. Okay, this is the next problem. So if you look at this formula, Z equal to A table isobar formula 2 plus AC divided by 2. In case if you want to quickly remember in CSIR NET exam duration exam, here 2 is there, here also 2 is there. Okay, remember this. Here A is there, here A is there, 2 divided by 3. So this is trick. So I'm going to substitute, directly substituting these values. All they are giving all the values. Okay, Z, they want to Z value. This one is 216 divided by 2 plus what is AC value? A suffix C value. So we need to convert this one. Okay, first 0.75 divided by this one is 2 AS, right? 24 into 2, 48 into 216 whole power 2 divided by 3. So in case if you calculate this one roughly, you finish the calculation, Z you can get 84. This is the answer. Like that they are asking any questions. Okay, so one more problem is there, this similar problem. So this one is very important. A nucleus of mass number A equal to 125, the binding energy calculated from the liquid drop model. So binding energy they are giving symmetry terms. They want to find the z values. Okay, so this you can try. Problem is a nuclei of mass number of A equal to 125. The binding energy calculated from the liquid drop model. So surface energy is 0.7 mega electron volt. Asymmetric energy is 22.5 mega electron volt is maximum for. So after looking this question, you can't get any idea about the stable isobar nucleus. You clearly observe this question here, what they are asking. So here they calculated binding energy from liquid drop model formula. So this is the important term. So therefore we can use this stable isobar formula for calculating the maximum values. Okay, so Z maximum, right? Z equal to A divided by 2 plus AC divided by 2 A power 2 divided by 3. So if you use the A value 125 divided by 2 into 0.7, 2 into 22.5, 125 into 2 divided by 3. It is better. I'm going to, this one is calculating here the 125, right? 125 divided by 2 plus this I'm going to write 7 plus 10, 7 into 10, 20 into 2 to 5, okay, into this one is 25, okay. This one is almost 125 divided by 2 plus 0.4. You cancel all these things, then you can get here 9. This one is 5. Okay. 125 divided by 2 into this one is 7 divided by 18. 125 divided by 18 and 125 divided by 43 into 80. That roughly approximately equal to 52.08. So this is the final answer. I hope you can understand this thing. The next class we are going to discuss nuclear decays. Or one more class is better to take previous year solution based on this stable isobar.